Okay, ji, Bismillah Rahman Rahim. Gentlemen, this is your 14 lecture, the audio recording of 14 lecture, and the topic is expression of restriking voltage or RRRV, rate of rise of restriking voltage. This RRRV is abbreviated for rate of rise of restriking voltage. Now, gentlemen, we have already defined this term. We have defined, of course, the arc voltage. We have defined the recovery voltage, and we have also defined the restriking voltage. And this is with reference to the previous lecture, that is lecture 13, where we have also drawn the graph of the figure of that particular RRV, that whenever the circuit breaker is open and the arc is about to be extinguished, then of course we have a transient condition, and the transient condition is such that a very high voltage can appear across the two terminal, that is the fixed terminal and the mean terminal of the circuit breaker. So the circuit breaker must be uh, prepared to deal with such type of high voltages so that restriking may not occur. The current may not to continue. If it is to be continued, then we will have for another half cycle, right? That is 0.01 second time. Okay, now the following figure shows fault beyond circuit breaker and an equivalent circuit where LC are the inductance, L is the inductance, and LC are the inductance and capacitance per phase of the system up to the point of the breaker. So now, gentlemen, you see here before the fault occur, this is the situation. Before the fault occur, we have a system here, and it is also represented by a parallel capacitor, and now we have a CB, that is circuit breakers. So this is normal. Now under normal condition, the capacitor will take its own current, that is IC. So the total current input will be equal to IL, that is load current, plus IC, that is capacitive current. Okay. Let's say, for example, fault occur beyond CB, beyond circuit breaker, the fault occur, and this is how the fault occur. You see here, just when the fault occur, this, of course, capacitor, which is shown in the previous figure, is of course shunted. So there will be no current flowing in the capacitor. The capacitor current will become zero because we have a zero parallel impedance. So therefore, the only current which will flow will be the fault current, and it will flow in the reactance and resistance of the transmission line. So this is the that particular figure which explains when the fault occurs. So what will be the circuit, or you may say parameters, or the circuit, how it behaves. Okay. Now, gentlemen, R is the in this case R is neglected. Neglect R because normally you see in the power system analysis we neglect R. So we have the following equation: L di by dt plus 1 over C I dt is equal to E. E is the applied voltage. Now, gentlemen, you might be thinking that E, which is the applied voltage or the system voltage, is not constant like we have represented it with a constant E. It is sinusoidal. But even a sinusoidal current, a sinusoidal voltage, is constant at any particular time. At any particular time, even a sinusoidal will have one constant value. I'll explain this point to you when I have an interaction class with you. If you understand, okay, but if you don't understand, I will clear this point in the interaction class. So this is the differential equation. This is the differential equation representing, of course, the scenario, that is when the circuit breaker is of course opened. So when the circuit breaker is open, the current is diverted to the capacitors, because previously when the circuit breaker, when the fault occur, there is no capacitive current, but right when the circuit breaker or the short circuit part is finished, and again the current is diverted through a capacitor, so it is flowing through a resistance, inductance and capacitor. By omitting the resistance of the circuit, which is a very little effect, we have only LC circuit, LC series circuit, LC series circuit, and this is represented by this differential equation: L di by dt plus 1 over C I dt, integral I dt is equal to. Now, gentlemen, the solution of this differential equation will give us the voltage across the circuit breaker. But why? Why? Because the voltage across the circuit breaker is actually voltage across the terminal of the circuit breaker. This is voltage across the capacitor. Sorry, the voltage across the capacitor is actually the voltage across the terminal, across the fixed and moving terminal. Uh, you may call it terminal, or you may call contact, moving in fixed contact across the contact of the circuit breaker. So basically finding VC is actually will be that particular voltage across the contact of the circuit breaker. And sometimes this voltage rises to a very high value, and that voltage we call as restriking voltage. And if restriking voltage is very high, it may of course break the insulation between the two contacts, and the current or the arc may continue for another half cycle. Okay. Gentlemen, you see here Q is equal to CV. So therefore, dQ by dt, that is differential of charge Q, is equal to C as a constant and differential of voltage. Okay. But let's say you see I, that is I is equal to C dV by dt, because differential of charge is current. Differential of charge with time is current. So therefore I is equal to C dV, C divided by dt, that is differential of voltage across the capacitance with respect to time. Okay. Now, if we take the differential of the current, if differential of the current, again differentiating, so it will be differential of the current, and if we take the differential of the current, it will be the second derivative of voltage with respect to time. So therefore, we are putting this value, that is, we are putting equation number 1 into the previous differential equation, that is this equation, right? Okay. So LC divided by dt, here in the original equation we have 1 over IC integral of I with time. So this is actually VC, that is it is representing. You see here, this is the voltage across the capacitance. This is the voltage across the inductance. The summation of this will be the total voltage applied. Okay. Now, so this is the differential equation. Now the solution of this differential equation, the solution of this differential equation will be actually the voltage across the contact of the circuit breaker. Now we have to solve any method you can apply to solve this differential equation, either classical method or Laplace transform method. But Laplace transform method is a very strong method. You will get solution in few steps of differential equation, and it will be the equation of VC with time. VC, that is voltage across the capacitance. As I have explained, this VC, which is the voltage across the capacitance, is actually the voltage across the contact of the circuit breaker. Okay, now you see LCS square and VCS. S represent the Laplace transform, plus VCS, that is the Laplace transform of the voltage across the capacitance, divided by the right hand side, which is E by S. that is differential of a constant voltage. So we can take this V as common, and in the bracket we are left with LCS square plus 1, and when we are shifting this to the right hand side, VCS on the left hand side will be equal to E divided by S, and to bracket the bracket LC square plus LCS square plus 1. Okay. Now we can take even LC common. If we take LC common, see the denominator is LC common. So this will be equal to S square plus 1 over LC. Now gentlemen, the natural frequency of oscillation omega n is equal to 1 over LC under root. That is from simple circuit theory. From simple circuit theory, the natural frequency of oscillation in radians, right? It is, of course, if we have to in second, that is f will be equal to 1 over 2 pi LC under the root. So shifting 2 pi here, we have omega n. So 1 over LC is equal to omega n square. So replacing this LC or 1 over LC with omega n, LC will be replaced by omega n square, because omega n is equal to 1 over LC under root. So therefore we have this omega n in the denominator, and there we have the omega n square. So naturally it will be shifted to the numerator. So this will be the equation, and now we can take this omega n s common. So in the bracket we are left with omega n divided by s square plus omega n square. Now this is a simplification, because we perform this simplification only so that we may take the inverse Laplace very easily. Now you can take inverse Laplace very easily, because if you see Laplace table, so this omega n divided by s square plus omega n square represent, of course, the integral of that particular function. That is, in the Laplace transformator, you will see omega divided by s square plus omega square. You will find this, and it is the integral of that particular sine function integral. So now this omega n by s, when you take this one, when you take this one, it will be omega n e s will be, of course, finished, because we are taking the inverse Laplace, and the inverse Laplace of this will be equal to 0 from 0 to limits and sine omega n t. Okay, so now if we take the integral of this, the integral of this will be equal to the integral of sine omega n t. So this will be minus cosine omega n t divided by omega n. So this omega n cancel with this omega n. We have yet to put the limits. We have not yet put the limits. And if we put the limit, we will get this VCT E 1 minus cosine omega n. Because if we take this common, it will be t minus 1. So if we just multiply this, then 1 will become plus, and omega n t will become minus. So it will be equal to E common 1 minus cosine omega n t. This is the voltage across the contact of circuit breaker, and is called restriking voltage. At the start of that, I told you that this is, of course, the derivation of restriking voltage, and the voltage across the contact of circuit breaker is actually the voltage across the capacitor is actually the voltage across the contact of the circuit breaker. So now we can put this relation also, that is omega n t is equal to pi. That is one thing. What we are finding actually, the maximum value, of that. So the maximum value of that will be only when cosine omega n t is equal to minus 1. When cosine omega n t will be equal to minus 1, then this minus will become plus. It will be E into 1 plus 1 is equal to 2e. So therefore, that particular angle at which cosine omega and that is cosine omega and t is 1 is pi, because at pi the cosine of pi is equal to minus 1, right? So now we have to put this, and this will be equal to like the simplification of this VCT is equal to E 1 minus cosine of y, and cosine of pi is equal to minus 1. So VT is equal to E 1 minus minus of 1 is equal to VCT is equal to 2E, twice the applied voltage, twice the voltage, so much high, twice the voltage. So its maximum value of its striking voltage is 2E. And now next we have to find rate of rise, rate of restrike, rate of rise actually, rate of rise of restriking voltage. Rise is missing here, you will put rise here, so later on, but this is rate of rise of restriking voltage. And when you differentiate this, right? Okay, maximum value of restriking voltage, rate of rise of restriking voltage is the differential of this. So if we differentiate this, the differential of 1 will be equal to 0, and the differential of minus cosine omega t will be equal to omega n and e sine of omega n t, right? So the maximum value will be, the maximum value of rate of rise of restriking voltage will occur when sine omega n t is equal to 1, right? So therefore the maximum value of R3V is equal to omega n e when sine omega n t is equal to 1, right? And you can calculate also the angle, at which angle of course it will be, that is the time from that is put omega n t is equal to pi by 2. From this you can obtain what will be the value of time or omega n at which it will have a maximum value. Okay. For a 132 kV system, the reactance and capacitance up to the location of circuit breaker is 3 ohm. 3 ohm is the reactance, right? Inductive reactance. And 0.15 microfarad, 0.1, it is the capacitance. That is not capacitive reactance, but capacitance respectively. Calculate number 1, frequency of transient oscillation. And number 2 are B, maximum value of restriking voltage across the contact of circuit breaker. And number C, that is third point, is maximum value of RV, rate of rise of restriking voltage. Now gentlemen, since inductance is not given in Henry, it should be given in Henry, but it's given in ohm, so it is to be converted into Henry. But C is directly given in farad or microfarad. So omega L is equal to 3 ohm, and L is equal to 3 divided by omega, and omega is equal to 2 pi f, and f is of course the normal power frequency 50 hertz. So with that calculation, we can get simple calculation. We can get L is equal to 0.0095 Henry. You can convert later on if you want in millihenry, but this is Henry. 0.00954 Henry. Okay. So number 1, frequency of oscillation, transient oscillation. So naturally this is resonant frequency. It's called resonant because we have resonant circuit. We have LC, that is resonant, not the parallel circuit, because so it will be equal to Fn is equal to 1 over 2 pi LC. That will give you answer in hertz. If you want answer in, of course, radians, you can of course use of course omega n. Omega n will be 1 over LC under root, because if you shift 2 pi to other side, it will be 2 pi f 1 over LC, and 2 pi f is equal to of course omega n, right? So therefore by putting these values, Fn, that is frequency of oscillation, will be 13.291 kilohertz, right? So now from that particular we have derived a restriking voltage, and restriking voltage, you can see that formulas from the previous article we just did, and Vc is equal to E common into bracket 1 minus cosine omega and t, and we have also already calculated the maximum value of this. Maximum value is equal to Vc, that is Vc is actually the voltage across the contact of the circuit breaker, so it is 2 E peak, because cosine omega t is equal to minus 1, that particular angle is of course phi, that way cosine omega and t is equal to minus 1. So 1 minus minus 1 is equal to 2e. So 2ep. Now actual numerical value of this is, now 2 is here, no doubt about that, and we have 132 kV system. So 132 kV mean line to line voltage, and all these calculations have been performed on phase basis. So the phase value will be equal to 132 divided by 3 under root. So this is RMS value. To get the maximum value, we have to multiply it by 2 under root further. So this gave us the maximum value, that is the time function, is 215.6 kilovolt, right? Okay, now maximum value of RRRV, rate of rise of restriking voltage, and from that particular derivation we have come to the conclusion that omega n is should be equal to or greater than this omega n e sine omega t, and uh, this is the peak value, and therefore we have uh, 2 pi fn, which stands for omega n, and e peak is of course equal to 132 divided by 3 under root and into 2 under root multiplied by 1000. This 1000 because of kilovolt because 132 kV, so we have used simple 132 multiplied by this 100 becomes volt. So after performing these calculation, we get 9010.45 multiplied by 10 raised to the power 6, or we may say 9010.25 megavolt per second. Per second, you see the rise, how much rise it is. And if we, okay, so it is 9010.45 multiplied 10 raised to power 6 volt per second, or it is equal to 9.01045 kilovolt per microsecond, right? Per microsecond, right? So you see how much kV, it should be simple, let's say 9 kV per microsecond. This microsecond, this is not second but it is microsecond. So how much the rise, you see how much rise it is. So this is a very, of course, a very high rise of the striking voltage, and all our circuit breaker must be strong enough to cater for these type of situation when it occurs. So, gentlemen, you just go through this article, numerical. Next time, if you have any question, we will clear all your question in that particular interaction time, inshallah, on Wednesday, 11 a.m. Thank you very much.